Good evening. Welcome to Krishna's classroom. Let us complete the characterization theorem today or tonight. We have already proved 1 implies 2, 2 implies 3, 3 implies 4, and the last lap is proving 4 implies 1. That means we assume X is a metric space with every sequence in X having a convergent subsequence. That's important. Every sequence having a convergent subsequence. Now we want to show that X is compact in the sense that every open cover has a finite subcover. So what we first establish is that the X is a bounded set. First prove X is a bounded set. So we work on this by contradiction. Okay. Suppose not bounded, then we can construct a sequence X with no convergent subsequence. We shall do this as follows. So fix an X belonging to capital X. Then we can choose Xn not belonging to which means if you take a ball of radius n around X with X as the center, then you can find an element outside that and call that X. Okay. Now this can be done for each n because we are assuming X is unbounded. Okay. Now let us look at the consequence of it. Take out this. So we now have a sequence constructed in this way. Xn we have a sequence Xn and by 4 it should have a convergent subsequence, say x and k. Then the sequence x and k is bounded. Why? Because it's a convergent sequence, so it is bounded. In particular, there exists capital N such that the sequence x and k is inside the ball of radius m. Ball of radius n centered around x. This contradicts our construction, the structure of Xn, or the way in which we have constructed the structure of Xn, namely this is that Xn does not belong to okay. So that is the reason. So that completes the proof of that it is bounded. That's an important observation that we make, and we now proceed with the major steps of the. So what do we do? What do we have to do? We have to show that if we have an open cover for X, then it has a finite subcover. So the next step is, so now proceed to prove compactness. For that, let U alpha be an open cover we want to show that there exists a finite subcover of U alpha for so for x belonging to x, see x is in some U alpha. It is in one of the U alphas. Okay. Now define Rx as the supremum of all R belonging to R such that V that means you are fixing x and with reference to x chosen from capital X, we take the largest or the greatest ball with center at R contained in the U alpha into which X belongs to. Okay, let whatever be the radius of that, that's what we are taking here. So this is the definition of Rx. So this we shall need over and over again. So let me just put in a block. So first we take up the case if Rx is infinity, belonging to X, then there exists a U alpha such that X. We shall prove this. Hence, U alpha is the singleton subcover for that means X is compact in that case. That is, it is a finite subcover. Now we shall give a proof for this statement that if Rx is infinite for some X belonging to X, then there exists a U alpha such that this holds and therefore you get a singleton subcover. Let's just indicate the proof of this. Now you see that since X is bounded, which we have proved in the just now that X is bounded, since X is bounded, BXR. Since Rx is infinity, there exists T greater than R and alpha such that comes from the definition. X is contained in B R and it is contained in B xt and because Rx is infinity. So there is a T greater than R and this is contained in particular. So what does it mean? For the particular alpha. That means we have completed the proof that there exists a singleton cover for space. Okay. Now we have to take the other possible cases. So we have considered the case where Rx is infinite. Okay. So now we take the case where Rx is now we claim that epsilon, there exists an epsilon positive defined as the infimum of all Rx for x belonging to x. This is positive. This is the assumption. That means the collection, you see, for each x, you can have a Rx. So you are given a U alpha. Then for each x, there is a corresponding Rx. Now what we are saying is that this collection of Rx is bounded below by 0. In fact, it is positive. This is the point. That is, epsilon is this is the assumption that we are making. Epsilon is defined as the infimum of all Rx when x runs over the entire capital X. Say that epsilon is positive. So again, by contradiction, if epsilon is not positive, then what do you have? Then you are going to have there exists a sequence of points xn x such that R associated with xn goes to 0. This is the conclusion that you can immediately take. Therefore, see, what about xn? Is an infinite sequence and by 4 has a convergence subsequence. Okay, let x and k denote this convergent subsequence. Now, since x and k is convergent, it converges to some x. So now x belongs to sum to u alpha for some alpha, because u alpha provides capital X with a open cover and each u alpha is open. Hence, there exists an R positive such that now for k large, enough, the distance from x to x so this is the situation you have. This is x. Now you have the sequence converging to x you have this is your R radius, this is Vxr. Now you can take a circle with half the radius of Vxr. Say this is radius r by 2. So this is your V r by 2. And what we are asserting is that since x and k converges to x, see that from some stage onwards all these x and k are going to be in this one. So x and k is somewhere here for some nk. This is your x and k. So what can you say about this? So now you take r and k. What is r and k? R and k is the radius of the largest circle that you can enclose in a U alpha. Okay. So R and K ball at x and k inside U alpha. Okay. Then you can see that the distance from x to x and k is r by 2. And you see that it doesn't go to the boundary of U alpha. So I think this is Vxr. This is the U alpha you are considering. So it doesn't go to the boundary. So you see that the distance from x and k to r. So some circle with radius. Therefore, you see that the result that you get is this is going to be the distance from x and k to the boundary of the largest circle enclosed in U alpha is going to be r x and k. So r x and k, r x and k is now greater than r by. That's a consequence of that. For k. Okay. So what does this say? This implies that what was our assumption? Epsilon is the infimum of all Rx x belonging to x. Okay. So this follows that this epsilon is greater than 0. That means this contradicts the assumption we have made that r x and k goes to 0. that is epsilon is now this is a consequence of the assumption that epsilon is goes to or rx goes to 0. So that is the assumption that we have made. So this is that therefore that is epsilon is greater than 0. So that is one part. Now we exploit this. So let that is epsilon defined as the infimum of, so I am just recalling the definition, Rx for x belonging to is greater than 0. Strictly positive. This is the assumption that we have. This is what we have arrived at. Now let us see what is the consequence of that. Now choose some x1 then choose x2 such that x2 does not belong to x1 that is possible. Now what do you do? Having chosen x3 does not belong to okay, so we have chosen x, started with an arbitrary x1, chosen x2 and x3 according to rules, and now inductively choose inductively choose xn such that epsilon by 2. That means, see, it's like this. You have start with x1, So this is your B epsilon by. Now choose a x2 outside. Yes. Now choose x3 outside x1 and x2. Somewhat. Okay. This you call bx3 and so on. So you choose the sequence x1, x2, x3 and so on. So these are the sequences that you have. This is x1, this is x2, this is x3 and so on. Okay. Now we claim that we cannot do this for all n. That means it should, at some stage it should end, finite stage. For if it does not, if we can do this for all n, then what would you have? Then there exists that we have constructed there exists in Xn as an infinite sequence. As an infinite sequence with no finite convergence subsequence. No finite subsequence. This is because T xn is greater than epsilon and epsilon is positive. Therefore, the distance between xi and xj or xm and xn is always greater than epsilon by, which implies x is inside some capital N so you have an epsilon by 2 net, finite net for x. It's exactly what you want to prove. Now what more you can say that, see, each one of these is going to be some u alpha, okay. Alpha k such that B contained in u alpha k. which implies okay, that is U alpha as convergent as a finite subsequence covering now you see from the definition of this, you see that from epsilon this Rx, you see that there is a U alpha k corresponding to xk such that bxk epsilon by 2 is contained in U alpha k. Right? And x is already equal to this. What does it mean? It means x is contained in the finite union of U alpha k. That means for the given covering, there is a finite subcover. So that shows it's a slightly lengthy proof with a lot of ideas put together. It is not something trivial, but it comes through various understanding of the structure of the U alphas and the points in X. Okay, so that completes the proof of this. So we have now completed the proof of the characterization theorem. So now let me just look at an example where possibly everything fails. Okay, so let us look at this example. Now we have already said that take S to be the sequence 1 by n with the usual metric R okay. Now you have already explored this and said that this is not compact. Okay, how do you construct a one of the most refined open open cover will construct? So consider, so let us minimum of and now you know that this is positive. All this delta I. Now you look at this one. So consider one by n minus delta n 1 by n plus delta n. Then you see that un contains only one element from this. Okay, only 1 by n is, so you see that S intersection un is the singleton 1 by n. The singleton 1 by n. And you know that this is also true, that S is contained in so un is an infinite, is a cover, is an open cover for S. Okay, that's quite easy to. That needs little bit to take care of the points that are lying close to or 1 by n with n becoming very large. You will have to find out a corresponding un. That is possible. That's obvious rather. Okay. Now you see that this does not have a subcover covering so this is the violation of condition 1. So 1 is not true and hence implies not false. Now we will examine the case 2 when this is about 1. Okay. Observe that is totally bounded. That is possible. For any epsilon positive, you can find neighborhood system which will be covered. And all that you need is you'll have to take a element like minus epsilon plus epsilon. So you take see for epsilon positive. Then what happens? The tail of the sequence will be taken care of that. For any epsilon positive can get taken, the rest can be covered by finite set of elements. So it is totally bounded. So S is or you have the other argument, totally bounded S is a subset of the interval 0, 1, which implies S is totally bounded. But now where it fails to become compact, this sequence covers or converges to 0, which does not belong to S. So S is not compact. So you see, the second condition, that it is totally bounded and complete, is violated in this case. So completeness is violated. Total boundedness is taken care of. Now if you want to get something that violates the total boundedness, then you can look at the Z in R with the usual metric. Okay. Now the third one, where total boundedness will be violated. The third case is that every infinite set has a accumulation point. Now S is infinite set with 0 as the only accumulation point. Only accumulation point. And 0 does not belong to another violation of 4. See that Sn S no convergent because every subsequence converges to 0. Zero not in S. Therefore, it is not compact. So we have given an example where all the 4 conditions are violated. Okay. So thank you very much. I think we wind up today, and that completes the proof of the characterization of compact metric spaces. Very useful criteria. Thank you.